How does Gödel, Bell, general relativity, and quantum mechanics relate to the ICT?
But because of those semantic relationships being written into the very nature of epistemology and cannot not be written into the nature of epistemology, then the proof applies to epistemology. The results of the proof apply to epistemology. It is inherent in the nature of the relationship between the subjective and the objective that we cannot have that relationship be both perfectly symmetric and perfectly continuous at the same time. Point blank, period, no exceptions. And why do I get to know that? Because of the rigor of the proof itself. And so you say, okay, wow, you just made a really badass claim. Like I walked with you, we did these steps, but that level of knowledge, that like what the fuck? And then you begin to see that actually this isn't the first time. This is the third time that humanity, maybe even the fourth time that humanity has encountered this. In fact, as you start to dig into it more, you discover, oh, wait, actually, maybe the fifth time. What are the examples of this showing up already happening? Well, one of the examples is way back in, I don't know, early 1900s, this guy by the name of Gödel. I'm hoping I'm pronouncing his name properly. I keep wanting to say Godel, but that was because I read it when I was by myself and had no tutors. So in effect, there was a mathematician that was essentially responding to this thing called I'm going to call it the Vienna Circle or the Whitehead Project, or this idea that mathematics could be unified, that we could essentially develop a body of math that was completely coherent with respect to set theory or logic or some set of axioms that would allow us to derive all knowable truths. That there could be a base of anything that is truth in math, right? Proof that is that one way or another, we're going to be able to connect these ideas, postulates or premises or axioms or however wanted you to set up as, we're going to take this constellation of concepts and we're going to be able to use these tools to manipulate them. And from that, we're going to know the entire tree of all things that can be known. And that was a sincere effort. It's like some people basically spent almost their entire lives trying to figure this out. And then this guy came along and he basically said, hey, if you define each statement in a proof in this sort of way, and I'm going to correspond a number, and then these numbers can themselves be related in terms of proofs. And all of a sudden, if we do this sort of meta argument about how the proofs describe themselves using this number system, we can create a contradiction. And the mathematics associated with that's pretty elaborate. I mean, it takes a fair amount of study to work through all the details. But the upshot is that you have a system attempting to describe itself, and when it does, it pops out this thing that basically says, well, this contradiction occurs, and the contradiction is written in such a way that you can't really have a hope that it would be both complete and consistent, i.e., mathematics be both complete in a sense that it describes all knowable things that are true, and consistent in a sense that it doesn't get anything that says something is both true and false at the same time. So in a sense, well, okay, when that person made that observation, it torpedoed the entire project, because it so happens that Gödel basically was careful in the way he represented that proof, and people studied it and they looked at it and they basically said, you know what, I can't find a flaw in this. This is airtight. It's a rigorous proof. We have to reconceive of how we think about mathematics. Now, at this point, a reasonable person might be saying, wow, why are you connecting the notion of this mathematician's proof and this thing called the incommensuration theorem? Well, again, it turns out to hinge on the definitions. What does it mean to say that something is consistent, i.e., that it can't be both true and false at the same time? Well, in effect, I'm basically trying to assert a notion of symmetry, that um, the truth that's held in the premises and the truth that's held in the transformations are going to allow us to know the truth of the outcome. So I shouldn't have, one derivation path starting with the same premises and going one direction and arriving at, point A. And then I start with those same premises and I use another derivation path, which goes through, another course and also arrives at point A. But one of them tells me the point A is true and the other tells me the point A is false. Right? That would be a violation of symmetry. It's the same context, but the content is different. One says it's true, the other says it's false. If the notion of truthfulness is a content, and the position A in the hyperspace of all possible proofs or all possible statements is essentially the context, then in effect I've violated symmetry. So the notion of consistency in mathematics cannot not be exactly equivalent to the notion of symmetry. And so what about this notion of completeness? Well, the notion of completeness would basically be like, think of the proofs as being like, again, paths through the hyperspace of all possible statements. And in effect, what we're basically saying is that starting in any position in that hyperspace, I can get to any other position in that hyperspace by following the paths of truth. And that there are no islands, i.e., there are no unreachable places, things that are true, but I can't get there from here. If all I can do is walk and I don't have a boat, an island is a place I can't get to. I'd have to use another tool like swimming or a boat or an aircraft or something. But if those tools aren't part of the picture, then the island is inaccessible. And if the tools that I'm using are methods of proof, and those tools can't get me to certain truths, then in a sense, I now have a system which is incomplete. It can't get to, can't describe, can't derive the truths that are on those islands, the statements that are true, but aren't true for a reason that we can essentially derive from the premises that we have using the tools that we know. That's incompleteness. And you'll notice that when I'm talking about paths of how to get there from here to there, that's a notion of continuity. Because any place that there's no path from here to there is essentially the very essence of what it means to be discontinuous. The land had a discontinuity in the water. You have essentially a place where the land stopped, the water began, and then the water stopped, and then there was land again, the island. The land was discontinuous, at least as experienced from the surface. Now, we all know that the metaphor doesn't allow for going underwater and stuff like that. But again, that would be methods beyond those available to us at the time. So is it the case that we can have a notion of continuity, connects everything, no islands, and a notion of symmetry, there are no contradictions, that every path leads to a place, and if there are multiple paths leading to that same place, that you're arriving at the same place, and the thing that you get there when you're there is the same. In other words, that arrival at a place is path independent. So in effect, it cannot not be the case. Now notice I'm using the strict form. Cannot not be the case that there's a one-to-one correspondence between the notion of completeness and the notion of continuity, and the notion of correctness, or in this particular case, non-contradiction, and the notion of symmetry. Complete and consistent. So in effect, I've now just established that the net result, the essence of the net result of Gödel's incompleteness theorem is in an exact one-to-one statement, making exactly the same statement as the incommensuration theorem. The ICT is a generalization of the Gödel proof because it's using a more powerful language and was a simpler derivation and covers more than just math. It's basically saying the same thing to change the course of the history of math. And you don't have to take my word on this. You can look it up. And so in this sense, we now have an observation of a version of the ICT showing up 100 years ago. And the same thing happened in, what was it, 64 or 67? There was this thing called the Bell theorem. And in physics, we basically were trying to come up with the laws of the universe, i.e., what's knowable as do the same laws apply everywhere, right? That's a kind of symmetry notion. But the thing is that people at one point were basically saying, well, can I conceive of physics purely in the notion of causation? Can I think about it in a sense of local influences? Remember, I mentioned way back in the beginning this thing called the Minkowski diagram, that influences can only travel at the speed of light or less. The causation can only move through the universe at the speed of light or less. And so, in effect, if I want to have something that provides predictability or utility in the sense of being useful in a technological sense, then being able to structure it purely in terms of causation is essential. But all of a sudden, we were having these phenomena in quantum mechanics of this sort of entanglement. So there's this real question: can we rework the notion of quantum mechanics that doesn't have this spooky action at a distance? Right? If you look that up, you'll see there was a huge amount of conversation around that concept. And again, I'm talking about it not in a popular sense. I'm talking about it in the essential sense. What was that debate actually about? It was actually about, can we transition from this apparently flawed model that incorporated this entanglement thing to a classical model, i.e., hidden variables, descriptions, and so on and so forth, that could account for the observed phenomena in a purely causal way. And those are called hidden variable theories. And so there was this observation. If we basically are looking for entanglement, and we're trying to test if there's a way to account for that entanglement in a way that is not in any way dependent upon these non-causal influences, then this inequality should show up a certain way in actual measurements. And it turned out that didn't work. That, in effect, there was this irreconcilable entanglement that could not be explained purely in any causal way. And there were lots of arguments about this. And it wasn't until something like 5 years ago that all of the loopholes were closed, that basically a version of the experiment was done that rejected the notion of things like superdeterminism, like maybe the entire structure of the universe is fixed, and there's therefore a correspondence between, the randomness of choosing to measure this entanglement in this way and this other one. It was like a lot of ridiculous ideas. But the thing is that there was this deep, desperate desire to both maintain the notion of causation, i.e., the principle of locality, and the notion of lawfulness, i.e., that physics could actually describe what was happening in the universe pretty much everywhere. Right? They didn't want to have a theory of physics that had exceptions, that, hey, it works in this galaxy but doesn't work in that one, or it works on this planet but it doesn't work on that one. Like, that's no good. Or that the laws are expressed in something other than purely causal dynamics, because if it was, then effectively the law is useless. So they wanted a set of laws that were both universal and expressed in the language of pure causation. But now comes along this Bell theorem and says, take your pick. You can get one or the other, but no theory of reality, no matter how conceived, can be both purely causal and purely applicable to everywhere. Either you give up the idea of lawfulness, you give up the notion of symmetry, or you give up the notion of causation, or i.e., the notion of locality. Take your pick. This was a choice that physicists had to make. The community was forced into a deliberation as to which of these things is more important. Well, because physicists inevitably are, in a sense, arguing from the third person point of view, they pick symmetry over continuity. They gave up the notion of continuity. They gave up the notion of causation as being the one and only way to describe models of lawfulness. They said maybe there's exceptions. Actually, no, there's definitely exceptions. We can't understand the exceptions in terms of causation. We have to accept that. But aside from that little niggling thing, we're going to talk about the laws of the universe in a causal way, and we're just going to basically just handle that as exceptions. And maybe we can leverage this into some sort of technological thing. Welcome cryptology and quantum computing and a few things like that. But the notion here is that the Bell theorem is essentially asserting, based upon actual experimental results, and again, unambiguous, uncontroversial logic, although, believe me, a lot of people wanted it to be controversial and tried to make it controversial. This was a debate that covered decades. Careers were made on this argument. And in effect, it's essentially saying that no theory of reality can be perfectly lawful and perfectly local. Well, what does lawful mean? Well, I already just mentioned that it's connected to the notion of symmetry in the fundamental sense. Same laws apply everywhere in the universe. The laws of content, anywhere in the universe at any time and position of possibility or probability, that there's a consistency of these regular patterns being observed. And so if we're going to say that there's anything that's knowable about physics, we're going to keep the notion of symmetry. And then, well, what about this notion of locality? Well, as I just mentioned, it's connected to the notion of measurement itself. It's connected to the notion of continuity in the sense that locality and continuity are the same. Go back to that notion of a discontinuous function I mentioned earlier. Right? I shouldn't have a situation where moving an infinitesimal distance in space results in an arbitrary discontinuity in the strength of the interaction or the field. Right? I can't have edges in the perfected sense in the physical universe. There's always going to be some sort of connectedness that's happening. There's no such thing as perfect disconnectedness. So in this sense, we're looking at a connection that is, again, indelible between the notion of continuity and the notion of locality. So in effect, the Bell theorem is essentially saying that no theory of the universe, no embodiment of physics knowledge can ever be correct if it asserts both perfected symmetry and perfected continuity. The Bell theorem is in direct one-to-one correspondence with the incommensuration theorem. That's observation number 2. Without going into the details, observation number 3, the mere fact that there is a theory of general relativity and a theory of quantum mechanics that, oh, by the way, has never been reconciled, right? There has been an effort by the best and the brightest minds the world has ever produced in the last 100 years. Not to say that people earlier ages were any less smart, but just that the people that even knew that this was a question, the very best and the brightest, have attempted to come up with a theory of physics that both held the truths of general relativity and at the same time held the truths of quantum mechanics and reconciled these two into some grand unified theory. You had the epiphenomenal and the sort of epicycle theory of strings, which after, I don't know, 30 or 40 years, people have more or less given up on, except for a handful of true believers. But they've never come up with anything testable. And then you have, a lot of these people that are trying to do quantized gravity, and you've got all of this stuff that's going on in CERN, which is, every imaginable theory. There's been something like 10,000 papers published on this topic of trying to reconcile quantum mechanics and general relativity. And after, I don't know, something like 50 years of the best and the brightest working on this problem, no one has been able to sort out even how to begin to solve this particular thing. Why? Because it turns out that one of them is describing time in a quantized, discontinuous way, and the other is trying to describe time in a continuous way. One of them is essentially trying to look at certain kinds of asymmetries. The other one's trying to look at certain kinds of symmetries. In every place that we see the conjunctions of symmetry, continuity, asymmetry, and discontinuity, that the conjunctions are just wrong. I'm not going to go into the details, but if you look into it, you basically notice that there's a reason why these two theories of physics, which have been thoroughly tested at the scale of the small and at the scale of the large, and yet in the middle, the only thing we can use is Newton, because at the scale of the small and at the scale of the large, they give us different answers. Why? Well, partially it's a reflection of this thing called the incommensuration theorem. It turns out it gives us a way to know that there is no such singular mathematical formulation that will bind these two foundational substrate theories. The math is inconsistent in the same sort of way that the Gödel theorem was pointing out earlier. And again, this is a instance, it's an observation of incommensuration theorem. Now that, by the way, is one of those things that once you see it, you can't unsee it. And in effect, what it does is it changes the course of literally all of the research that's being done. It basically changes the very meaning of what it is to do particle physics. We no longer can look for it as a physical or mathematical description. We can only reconcile it at a metaphysical level. So when the philosophers were essentially kicked out of the discussion some 50 to 100 years ago, right, back in the 70s, progress in physics stopped. And I'm not the first to have made this observation. It stopped. It's been dead in the water for 50 years. And so in a sense, we've now just basically said something that is at least as profoundly important as anything that has been said in either the Godel theorem or the Bell theorem. We've again basically said, hey, the notion of what it means to know reality is constrained in this specific way. We can know the nature of the constraint. That does not give us an ability to arbitrarily transcend it using the tools of math. And this is a hard thing for people to hear. Almost everybody rejects this. It's essentially something that goes against the grain of what people wanted to do back in, the early days of like I said, the 19th century or 1900s rather, that there was this deep impetus. People really wanted to come up with a grand unified theory of mathematics. If you could do that, you would have had your name in the history books for the rest of time, right? You would be infinitely famous forever, at least as far as Western culture would ever keep track of such a thing. And then, if you were able to come up with the theory of physics, which unified quantum mechanics and general relativity, a quantized gravitation, or a string theory that worked, or any other bizarro idea that someone had managed to come together, again, you would have had the highest level of prestige that is possible to have, because you would literally have outdone Einstein. You would have outdone Newton. You would have outdone literally every other physicist, the best and brightest that has ever worked on these problems in the entire world. Wow, that is a thing to put on your resume or whatever in your CV, right? So here is this weirdo, myself, coming from way out beyond the beyonder, like beyond the edge of the being itself, and essentially saying, oh, by the way, there's this thing called the incommensuration theorem, and it's just letting you know that that's just not going to happen. Obviously, this is not going to make me very popular, and at this particular point, I imagine that most people are steadfastly avoiding this particular body of knowledge. This is why there's never been a presentation in the physics community, certainly never been a presentation in the mathematics community. I'm just basically sitting around waiting for someone to notice that this has happened.